You guys have any questions so far? Like from the previous lectures? Okay, so whenever she went for Pedro, yes, we can start. So where are we? I think last time, right? Last time. I think last time we managed to define the canonical divisor. Right? So for this, what do we need? So we needed R. Well, first of all, R has to have a canonical module. Right, so we know that very generally, I think if R is S1, this is an S2 module. So if R is an integral domain, then we can say that it also has rank 1. But to define the rank, R has to be an integral domain, right? Because the rank is the dimension as a k-vector space once you localize at 0, where k is the field of fractions of R, right? So let's say k equals the localization of R at 0. And remember, this means that it's abstractly isomorphic to k. And this is true just because when you do this localization, what you're supposed to get is omega k. Right? And this is a field, therefore regular, therefore Gorenschain. That's fine. Okay, and so if we further add normal, right? And so we spent a big deal of a lot of time talking about this. If R is normal, remember this means R1 plus S2. With this hypothesis, then we can combine these two hypotheses into saying that omega R has to be R of some divisor, right? In other words, omega R is completely determined by what it is in codimension 0, which we know just to be k, and what it is in codimension 1. And that codimension 1 is recorded into a divisor. And that divisor we denote by kr. And this is a canonical divisor. Canonical divisor, this is the canonical module, right? And so you see the beauty of this, right? Because this may look mysterious in a sense, right? It's just this module that has magical properties. But to know what it is, all you have to do is to remember a finite number of prime divisors over R and a whole bunch of numbers attached to them. Right? We know that this is going to look like some finite sum right? These are prime divisors. i.e., you know that R negative pi is going to be a prime ideal of height 1. Right? And so you see that when you look at the prime ideals of your ring, you have, well, R is an integral domain, so there is only one prime ideal of height 0, namely 0. And then there is a new hierarchy of prime ideals, which are the height ones, the prime divisors. So all you have to do is to remember some of them, right? Who knows what it will be for a specific ring, right? But So you remember them, and then you remember some multiplicities. So the AIs are integers. And so you get to see that the structure of the canonical module is rather simple. Oh, right. So that was the whole thing of last time. To be able to cook up this object. And so thanks to this, dealing with the canonical module is going to be simple. And so it's going to be fun, and we don't need to be afraid of it. So today we start the last section. This very long chapter, which I hope is going to be the very last preliminary chapter. From now, there will be F-singularities only. So yeah, the only true preliminaries to talk about F-singularities are normality and Kahima-Collie notion. But let's say Gorenstein too, all these other things. So it's about pullback of divisors and the brilliant Schritt's correspondence. I'm sure I'm missing. No, it's like that correspondence. So, which is a very simple but powerful idea. So, to start talking about this, we're going to take a finite expansion of normal integral domains. Of course, we want to apply this to Frobenius itself, right? But let's look at this in very generally. So we, as usual, will denote by F the corresponding finite cover. So you most definitely have studied the structure of this type of maps in your commutative algebra class. Every commutative algebra textbook will have a chapter dedicated to integral extensions, finite extensions, and the structure of the map in the spectra. So what are a few things we know about this? We have this is the set of theorems, the line over, the going down, the going up, and all these sort of things. Which sort of show that this is a proper morphism if you use terminology of algebraic geometry. But for example, we know that this is surjective. This is line over every prime ideal of R, there lie a prime ideal of S. Okay? What else? This map has, what are the fibers of this map? If I take a prime here and I look at the inverse image, it's a finite set of primes, right? If I look at the inverse image of P, it's a finite set of primes. For example, so the picture to have in mind is that you have the spectrum of R over here, and then the spectrum of S is unfolding over it. Right? You can look at a fiber, and you're going to intersect and find the middle points. And the height is respect, and a whole bunch of things. You know, if you want to know the whole story, you should go and look at a chapter of every commutative algebra book that has the title Integral Extensions. Okay? So yeah, let's just put it there. And also, we're going to say that L over K is a corresponding finite extension of fraction fields. Actually, let me write it down as follows. So, where's the eraser? So let me write it out like this. So we're going to have R inside S, but R is inside its field of fractions. R is normal, so this extension here is integrally closed, meaning that every element here in K that satisfies a monic equation or say an integral equation with coefficients in R has to be in R. Okay. So for example, yeah, let's just say that. So here you have F. Okay. So this is the corresponding extension of fields. It's a finite extension of fields because this is finite. Okay. Now let's actually this extension here, right? What is R? R. So actually, what I want to say here is that this is a fiber. This is Cartesian. So i.e. L is the localization of S as an R module over here with the field of fractions. And it's part of these sort of things because, so here you have the zero prime ideal. And so the only prime ideal line over zero is zero. Okay, so it also suffices to invert element of R, to invert all elements of S. And that's an exercise that you want. And so you have this. So this is the height zero picture. Right? Beautiful picture, and that's what you get. In height one, we're going to have a similar story. So I can take P to be a prime divisor. And so I can go ahead and localize this extension at the height prime divisor. So remember here we have this notation. I write Rp for the localization of R at the height one prime ideal representing P. So here we have the corresponding localization. So this is the localization of S at that prime ideal. S is an R module. So I can localize at every multiplicative close of set of R. Right? So we get this is finite. So what is this ring? This ring is a GVR because R is normal. If you localize at every single prime divisor, what you get is a discrete population ring. What is this? Well, this ring has to be semi-local. What does semi-local mean? Semi-local means that it has finitely many maximum ideals. Why is it semi-local? Because it is a finite extension over a local ring. And because of all these structure theorems, we know that finite extensions of the local rings have to be semi-local. There has to be finitely many prime ideals over a maximal ideal. Okay? So this is fine. What is the dimension of this ring? It's 1, because it is a finite extension of a one-dimensional ring. And moreover, it's regular because it is a localization over S that only see height 1 point. So this is a Dedekind domain. What is a Dedekind domain? It's an Ethereum regular ring. Well, I guess regular is a regular ring of dimension 1. That just happens to be semi-local. So in fact, what this implies is a principal ideal domain. So in fact, this ring can be written as follows. It's an intersection of the localization of S at certain prime divisors. So here, the Q1s are the prime divisors of S lying over P. Over P, there will lie finitely many divisors. They have to have the same height. They will have to have height 1 because the height is preserved in finite extensions. It's the going down, going up theorems put together. Okay? So you get these prime divisors. These are DVRs. Each of them is a DVR. and the intersection of them is going to be this delicate domain. Each single one of them is going to be principal. Well, this is a PID, and so you get that. So in particular, so you can define these maps. They are not finite, but there are certain extensions. Right? How do you define these things? Well, it's through that, right? Because this thing here further maps to every single one that is contained there. Okay? So that's the picture in codimension 1. So again, the picture, if you want, is that you have the spectrum of S unfolding over the spectrum of R. And all we did was to look at a prime divisor P, and we look at all the prime divisors lying over Q4, I guess, at this point. So the spectrum of base SP, so this whole fiber here is the spectrum of SP, but every single one of these points represent the spectrum of SQI. So the whole collection of them together is this fiber. So the spectrum of SP is going to contain every single one of them. So if you localize further or one of them, you get the spectrum of SQI. Okay, that's sort of the geometric picture to have in mind here. And so this is extension. This is an extension of DVRs. They share the same field fractions. So this one is contained in L. The field fraction of this one is L, and the field fractions of this one is K. So I'm also saying this because you may have seen this in terms of ovulations. You know that if you have an ovulation of L over, if you have an ovulation of K over that ovulation, there will be finally many ovulations of L. It's just the same thing, but written down with divisors. So okay, you have this extension of DVRs, and you have this, and so well, let's isolate it again. So let's put it here. So this guy will have a uniformizer. What is a uniformizer? Let's write it down as T. So the point is that T generates the maximal ideal of this guy. So how can we call it? Let's just call it like this, right? It's the maximal ideal of this ring. It's generated by one element because it is regular. So in fact, this T can be taken to be any element whose valuation is what? T such that its valuation is exactly 1. Okay? So this is the uniformizer, or a uniformizer. So why this is important? Because then you can see where it goes here. Well, it goes to T, let's say, but then you can look it up as an element here. And you can compute the evaluation here. But it won't be 1. It doesn't have to be 1. What is it? Let's write it down as EI. And this is the ramification index. Okay, so if you go back to this picture, well, I wrote it in a very precise way, but I could have done the following too. And then we have look at the point here, expand it. And then we have look at the point here. So in a point here, we have ramification. You see, the expectation is that you go 4 to 1, at least this picture, 1, 2, 3, 4 to 1. But there will be points in which you will have a 2 to 1 situation. You have to count multiplicities. And that's what these numbers count. Okay. So this is the ramification index of an extension of DVRs. It's supposed to tell you if you have some ramification. Okay, like in algebraic number theory. Maybe you took a class in algebraic number theory, and if you did, you saw all this day one. Maybe day two. But it's a classic thing that also works in algebraic geometry, the theory of curves and so on. So you have this picture, so right? Okay, so you have at every single QI, you are going to have a ramification index. And that's all I need you to remember. So, any questions so far with this? For example, you will see that the extension is unramified if the ramification index is 1. Because what that means is that then a uniformizer of here becomes a uniformizer of this one. So on. Now, this is all we need to define pullbacks. And so here we are. Then we define the pullback of a prime divisor. The pullback along F for a prime divisor is by definition the following divisor. By the way, this EI is definitely at least 1. Exercise, I guess. So you see what the pullback of a prime divisor does, right? All it does is to record the ramification indexes, right? It tells you what is going to be the ramification index at every single prime divisor line over. Over Q1 is going to be E1, over Q2 is going to be E2, and so on. It only keeps track of that. You remember the last time I was telling you divisors are just a bookkeeping tool. And this is the bookkeeping you are doing here. You're just doing bookkeeping of ramification indexes. That's it. There is nothing mysterious about it. Okay? So you have that. And so using this, you can extend it to a homomorphism of abelian groups from divisors of R to divisors of S. How do you do that? By linearity. Right? Remember that this is the free abelian group generated by prime divisors. Right? This is the free abelian group generated by prime divisor of S. If I have any function whatsoever from prime divisors to divisor, that automatically define a homomorphism just by extension, by linearity, right? This is just a formal sum. So something here will be a formal sum. So this goes to AI pullback of PI, right? So therefore you get a homomorphism of groups. Moreover, you remember that. So if I do, my coefficients are integers, right? But I can have coefficients over any array I want, right? This means that these i's are just elements of the ring, and everything is fine too, right? So you get this homomorphism. Is this okay? Why
is the divisors preserve the orientation between R and S?
Preserve what, sorry?
The orientation of the, like, for example, we have R and S, and if we take the spectrum, it changes the direction, right?
Yeah.
Why is it that in the case of the divisors, it does preserve the direction between R and S?
It is a pullback. So yeah, you're right that there is the morphism of, let's say, of the schemes or topological spaces goes like this. But then, like the pullback goes this way.
Oh, okay. So
it's just a general thing. Yeah. You have a divisor here, an object here. You want to pull it back. but certainly some sort of extension of a scalar sometimes, because that's what you do here. And there are push forwards that go the other direction. Okay, so you have this. And here is your first exercise for this section. So remark, by remark I mean exercise. What happens if you try to pull back the divisor of an element of R? This is, let's take R to be an element here. It's just a meromorphic function on the spectrum of R. And so what do you think this is? I claim that it is principal, and it's a divisor over S of R. But now as R viewed as an element of K. So principal divisors pull back to principal divisors. Okay? So sometimes in an algebraic geometry proof, you may look at this notation. Like you pull back the local equation. But we don't do this here. And so what does that mean? If D1 is linearly equivalent to D2, then their pullbacks are linearly equivalent on S. So what does that mean? It means that the homomorphism of divisors induces a homomorphism on the divisor class group. Exactly. Homomorphism of groups. And moreover, you have the corresponding pullback on the Picard group. So I said that, of course, we want to apply all this to Frobenius. What do you think is the pullback of Frobenius? It's another exercise for you, but let's try to guess. So by definition, we have to look at a prime, well, it's suffices to do it for a prime divisor, and we have to take the uniformizer, and we have to extend it along Frobenius. So you're going to have T goes to T to the Q. So uniformizer goes to uniformizer to the Q, so the evaluation of T to the Q is Q, and that's all you remember. So here you're going to have QD. What you do is you multiply by Q on your divisors. Okay? So, and you see that here we've been pulling back divisors, right? So you may want to compare, but we also know how to pull back modules, right? This is a module. I can pull it back. By definition, this is S tensor RRD. It's just extension of the scalars. There's a canonical morphism to S pullback D. If you give me an element here and the usual multiplication, I can hook up an element here. This is reflexive of rank 1. This is of rank 1, but it's not reflexive. What do you think is the relationship between these two things? It's reflexification. This object here, I actually define it on purpose to be the reflexification of that. Right? I already know how to pull back this object, right? And these are the objects I actually care about. The divisor is just a bookkeeping tool. Right? These are the objects I care about. But I notice that when I pull it back, using the algebraic definition, which is just base change of scalars, I get an object that certainly has rank 1, that's great, I can put it inside the field of fractions, but it's not reflexive. So I lose my reflexivity. So what do I have to do? I have to reflexify. And reflexifying means that I should get an element that is S of something. And the question is, what is that something? What is that? But I define it for this to be true. So this is the exercise is that this is reflexification. In other words, that it becomes an isomorphism after you reflexify. Okay. So that's important to do. Okay. Any questions so far with this? Exercise for you. How do you prove this? You prove this is an isomorphism? You got dimension one. Where it's going to be triggered from the definition. And then the magic of the formalism of reflexification in S2 models and blah 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 lets you conclude. Okay. So you should never try to do anything here by brute force, and I hope anything in life by brute force. Okay, you just try to use the formal properties of things. Okay. Another remark is large exercise. Let's call it projection formula. It's the following abstract nonsense. So let's take any homomorphism of rings in the world, and let's call F the spectrum of theta, which goes from spec S as usual to spec R. And so let's take here a module N, and let's take here a module M. Both of them finally generated. So there is a canonical map that goes as follows. You can push forward N. In other words, we are just viewing N as a module over R by restriction of the scalar. So this is always a dumb operation, but conceptually it's important to keep track of it. Especially because in algebraic geometry it's very, very important. Okay, so let's keep it here. Let's do the tensor product with M. That's a perfect reasonable thing to do. But on the other hand, you can pull back M, and then you can look at the potential product over S. Right? There is a canonical map from here to here. From the universal property of tensor products. Well, if you want in practice, we have here like n tensor m over R, you send it to n tensor m. Well, here you have an S, so let's say it's more like n tensor m goes to n tensor 1 tensor m. Okay. So you have the map is super canonical, and so the projection formula says that this is an isomorphism if so actually the map doesn't require M and N to be finally generated, but the result requires them to be finally generated. And I'm going to require N to be flat. Since it is finally generated, remember that this is able to say that it is projected, meaning it is locally free of finite rank. Okay, but so let's say I like to say flat because it also is the shorter one to write. That's the projection formula. Okay, I'll let you do it. Now let's come back to the case we care about, and so let's still work in this context. Maybe we can do it here. No, let's do it over here. Let's do it over here. So let's move the camera. And by the way, it's not true, time is not flat. You can hook up a counter example if you want. So, in the same case, suppose order that what we have R to S is a finite extensions of the normal integral domains. And let's say that N is SE and M equals RD. Okay? So we have a map that goes from, we can push forward SE, and we can go ahead and tensor it with RD, and we can compare it to the Frobenius push forward of, okay, in principle here, actually, sorry, now I can see a typo here. Well, here's a typo. So for this to make sense, I need to add a push forward here because I want to say this is an isomorphism of in the category of R modules. So I gotta push forward. Okay. So if you go and Google it, that's the way you're gonna see it. So I have to push it forward and I have to compare to SE. I guess you see it starts to get ugly. So I'm gonna tell you what it is right away. So here I'm gonna put pull back. Am I missing a parenthesis? Yes. Just like this. Right? So, and what I'm gonna claim here is that this is a reflexification too. Okay? So here, technically speaking, what I'm doing is to take SE, tensor the pullback of RD, right? That's what gives me the map. But then I can reflexify this side. And then, by what I just told you, this becomes, well, first of all, this object here is going to become R pulled by D, and, sorry, S, over S. And then, the further reflexification means that the two divisors come inside as a sum, right? This last part is something we saw last time. So when you reflexify. So here, you have a very ugly thing. Sorry, one minute. So here we have a very ugly thing, but then as I reflexify it, it becomes a pretty thing. Okay? And so this pretty thing, I claim is a reflexification of this, which is this thing here. So the claim is that this is a reflexification. In other words, this thing here is a reflexification of that. Or the S2ification. Okay, and so how do you prove that? Because it's an exercise. All you have to do it is in codimension 1. And in codimension 1, it's going to become the projection formula. Okay, that's how you prove it. You have to prove it in codimension 1. That's all you have to do. And in codimension 1 is exactly the projection formula. So you extend it to the whole thing, thanks to the formalism of reflexification. Okay? So you see this applied all the time in the context of Frobenius. We're going to do it in a second. Okay? So usually but very often, especially old papers, like by all I mean like 10 years old, 20 years old. In the preliminaries, people always have this remark for Frobenius. The projection formula is for Frobenius over normal varieties. So let's do it right now. So why are we doing all that? Is because of all. I like to call this plasticity of the home. So, and this is the conclusion. Then what's what I want to understand? All I want to understand is the home in between SE and RD. Right? We are obsessed with homes. So I have the homes in between these two things. So over here, I'm going to have a similar looking home set. And so I call this plasticity because here you have a whole module of maps, right? This is a home set. And here my target is RD. Okay, what I claim is that there is a plasticity property that I'm going to write down in the sense that you can take the maps here and then you can remove the D. You can, you know, like if it were a Play-Doh, you can just mold it as you want. It's plastic. And so you can put here R, for example, or any device you want, but I want to go from D to 0, and then you can play with any device you want. I go from RD to R. Okay? But the price to pay is that. So for example, think of the case in which this is an effective divisor. So here what I'm doing is literally restricting the domain, because if this is effective, then R is inside there. So I'm sort of restricting my domain, my codomain, no, my domain, my codomain. And so, but I can do it and restrict my codomain appropriately by the pullback of D. Okay? So you can go ahead and move D to the other side. You can pass it to one side to the other. In this way. Okay? So you see that this is what I'm saying, these homes that are plastic. They have center plasticity in which you can play with them, you can move things around and have the exact sum of objects. So what I'm claiming here is this file. Technically speaking, I guess I should say that these are isomorphic. I honestly think of them as equality. For me, these are the same thing. How does this work? Well, if you have a phi here, let's take a phi here that goes from here to SE to RD. How am I gonna get rid of D? Well, I'm gonna twist by its moral inverse. So I'm gonna send it. Well, let's take so phi tensor R minus D. What is this? This in principle is this. It's very ugly. But what happens if I reflexify? What happens if we apply the reflexification functor? This becomes, so in particular, phi tensor R negative D reflexify becomes what? What does this have to do reflexify? By the previous exercise? It's gonna be F push forward S of E minus the pullback of D. And what does it become after we reflexify? R, exactly. And that's the map you get here. So the map in this way is phi goes to phi tensor R negative D, which is the unrestriction part. And then you reflexify. And because these two maps, these two homes are S2 maps, there was an exercise, homing into anything that happens to be S2 is S2. And so all that matters is what happens in codimension 1. And so you get the map in this way, and what is the map the other way? It's the same thing. If you have phi here, you send it to phi tensor RD, reflexify. And these two operations are inverses of one another. right? Is you take your fees and you really, I think of them like you play with them. You just fold it with your hands. You can move things from one side to the other, and you don't lose any information. Okay? It's a balancing act, and you get the exact same Helm sets. Well, isomorphic, I guess, but it's really canonical. Okay? And so this is based on the projection formula for this specific step. You see? Here you apply the projection formula, and it's a very canonical thing. So in the remark, I put a remark here that I can say what it is in words. Is another way to think about it. The other way to think about this is that you can look at these two Helms generically. You can localize at K, or you can tensor by K. And literally, these two things becomes Helm. They are literally the same thing. Because everything here, like SE minus F, pullback D, RRD, when you localize, they become, well, either L or K. So you have literally, so these two objects live inside there. Actually, for example, you can think of this Helm set as something inside here. These are the maps from L to K that sends SE to RD. And the same thing for the other one. And you can see that the same set of map that sends SE to RD is the same set of map that sends E minus pullback D to R. It's just that. So that's another way to say that this is actually an equality. Okay, it's just change of perspective, but it's the same sort of data. It's equivalent data in how you prescribe maps. Okay. So, but I guess this is also something for you to meditate about. Take your time. So actually, personally, I remember I got to understand this in a flight. I remember I was going to Costa Rica for Christmas, and it was a flight from Orlando to San Jose. And I remember like this looked very mysterious to me. But then I decided to really sit down and write things down explicitly. And it got to me that this is actually a very trivial thing to say. And instead that it's just moving things around and change the domain for the codomain. And write down what everything means inside here. Okay. So, but okay, we have that isomorphism that is very important, especially when you apply to Frobenius. And I guess that's what we're about to do now. How are we doing with the time? Yeah, it's good. Okay, now let's invoke back the canonical models. Now we have, sorry, this thing, we have this thing. And remember that we have this very important hypothesis, which is to say that we have an isomorphism like this. Okay, this is a hypothesis. That is mild because it holds for varieties and it holds for local rings. Generally, generally we have to put here something else. You remember? They are not isomorphic. They're only isomorphic after you twist by some invertible module. But for local rings, this is trivial. And with varieties, since both objects are defined over a common base K in a proper way, then you can sort of arrange this to happen. Okay? Otherwise, it's a hypothesis. Okay? So why is this a hypothesis? Because then you know that, well, formally there is a trace associated to this. Right? This is the growth in the trace. This is abstract. This is the trace. This is the co-unit of the adjoint relationship between upper shift and push forward, right? And so here you have this trace. It's a very abstract trace. But now, if you have this, you can write this. That's what we were calling the trace the other day. And And actually, I would like to clarify a mistake I made the other day. It's not so bad, but it wasn't very good because I needed the assumption that, well, in this case, S is S2 for it to hold. Let me tell you why. So I said, I think when we're talking about traces, like this trace here, that so this map generates a home set between here and here. So let me, but it's not true unless X is S2. Why? Because what you're going to have is a commutative diagram as follows. So here you have S, and here you have the home set or the home module between omega S and omega R, right? So this home set literally tells you how the canonical modules talk to one another in this category of points, right? So it's very important, right? Because omega R knows everything about R. It's the most important object attached to R. It's the heart of R. Same for omega S. And so here we're seeing how R and S talk to each other, talk to their parts. Okay? So this is a very important thing to understand. And I was saying the other day, okay, I can send 1 to the trace, and I said that this is an isomorphism, which is not true. Okay? Unless S has 2. Let me explain why. How does this work? So, and you see, this is important because it's sort of telling you that there is only one way in which they can communicate essentially, is by the trace and the multiples. You see? You see the beauty of it, right? It tells you something deep about how can you go from one to the other. It's only in one way. Okay, so on the other hand, so what you're gonna have here is something like omega S, and in principle here I should put omega R, and these two things are equal. I could put equal, right? Because what is behind this equality? Is the formal property between the adjoiners between upper shrink and push forward, right? This is the equality of homes that come from adjoiners. I could just write equality, but let me put an isomorphism. And I'm going to put an isomorphism because I'm going to replace this upper shrink by omega S. Because of my hypothesis. That I'm going to choose omega S essentially to be the upper shrink of omega R if I can, at least isomorphic. But then you have this map from here to here, right? Which sends 1 to the identity. And this map is an isomorphism exactly when S is S2. The fact that this is an isomorphism is the same thing as S being S2, which is our case because we're working with a normal ring. And normal means R1 plus S2. So, yeah. So this is somewhere in the notes throughout very well explained, I hope. And so we have that the home between omega S and omega S is this only multiplication by elements of S. And so this map here factors like this. And so this map is an isomorphism where S is 2. Okay, so that means that this little guy is a free generator of this S module. Okay. So because it works like this. And in the notes, when I made the mistake, I said that these two things, so that this is a generator, and it follows from growth equality, but essentially because growth equality manifests right here to say that this is an isomorphism. And I had in mind that this home set is S. But it not only holds if S is S2. Okay? In a sense of my hypothesis, usually this is written down if you see in computer books in the case of Kohema color rings, which are super, they're SK for all K. But anyways, we have this, and that's going to be very, very important. Because what I'm about to tell you Okay, like what I'm saying here is like there is only one way in which canonical modules can communicate. And I'm going to tell you that the way in which any other devices communicate to one another is by going through the trace. So the trace essentially knows the ways in which all devices can communicate to one another. So let's see that. Okay, we have that. And so let's do the following calculation. It's a very pretty one that you should keep in your hearts. It may show up in your. Are there qualifying exams here? You have to pass exams to pass your candidature for PhD?
Oh, yes. Like in the third semester.
Okay, if I happen to be your committee, maybe not for better because better is finishing. Did you pass it? You keep an I may ask you exactly this computation. If you happen to choose me, I'm telling you in advance what I'm going to ask you. So, it's really important. Look, let's come back to what I want to understand. I want to understand that, right? I want to know how two devices, one in E and one in D, will talk to each other. Okay? So, the first thing we know is that by this plasticity, I can put D on the other side. Like that. Right? Now, what I'm going to do is to, and I'm writing these isomorphic, but again, these are equalities. So the other thing I'm going to do, I mean, I cannot write equality because these things are not equal, right? They live on different worlds, but they carry the same math. So they're mathematically equal, something. Okay, so by adjointness, I can remove my pull forward here. Oh, sorry, I forgot an S here. So I can put E minus pullback D, and here I'm going to have, I missed one step. Okay, sorry, one more step. Plasticity. Now I want to put the canonical divisor somewhere. So what I'm going to do in the next step, let's say, or I could have done it here. I'm going to play with this plasticity I'm talking about, and so what I want is to have the canonical divisor on this side. So I'm going to put the canonical divisor here, but I have to pay the price over here of doing that. Okay? I can enlarge or enrich, let's say, because I don't know if I'm enlarging or not, because I don't know whether or not this is effective. But let's say I can enrich over here if I enrich over here appropriately by the pullback, right? So this is this plasticity that I can just pull things here as I wish. Okay? You with me? So now I'm going to use the adjointness. And I'm going to pass everything to S. I'm going to remove this push forward. So here I have minus the pullback of D plus the pullback of the canonical divisor. And here now I have to take the upper freak. If I remove the push forward here, I have to put an upper freak over here. This is RKS. So should I do it in the next step? I think you're fine, right? If I just say, okay, this is SKS. Okay, and so this whole thing here by this plasticity is going to become KS minus this. I can either put the KS over here or take this whole thing with a negative sign and put it in front. So what this has become is as KS minus the canonical divisor plus pullback of D minus E. And I'm going to denote, okay, I don't have enough room over here, but so this is what we have so far. And so you see what I'm saying, like actually I know that this Homestead, which is conceptually rich, right? I know that it has rank 1, I know that it is S2, so it has to be S of something, right? And the something is going to be the like the computational counterpart. And I'm telling you what it is this divisor. Conceptual, computational. You see? So I understand what this means, right? But I want to calculate things with it, and it's going to be this. Okay? So let's continue on the other side. And of course, we're going to apply this to Houdini's and see what happens. And because of actually, this computation is why F-finiteness is so important. Okay, so far, actually, let me write down the following. I'm going to denote the canonical divisor is this Ks minus the pullback of Kr like this. And actually, for some reason, now we're going to call it RAM. It's because in the finite case, the canonical divisor happens to be the ramification divisor. Whatever it is, let's take it to be that. Is what is the difference between Ks and the pullback of Kr. Okay? I'm going to use RAM somehow. So I just told you that maybe I should write here like the ramification divisor of F. But yeah, it's or we can use this one. I don't know what. Let's use RAM. What do you prefer, this one or RAM? In the notes I wrote RAM, but then let's use RAM. Okay. So RAM, ramification divisor, plus the pullback of D minus E is isomorphic, and actually I'm going to tell you what the isomorphism is to this. How does this work? How is it that just this gives you that? It's through the trace. You just have to go and look at what is every single here, and it's the following. So first of all, okay, explicitly. So we had the trace, right? We had the trace of omega r. In principle, it's a map that goes from here to here. So the first step is to apply the plasticity here. So I'm going to think of the following map. I'm going to think of the trace of R. Actually, I can do it to any RD. When I denote the trace of RD, it's going to be by definition. I'm going to take the trace of omega R, and I want to get rid of KR and put a D in here. So I'm going to twist by negative KR, and I'm going to add D. And I'm going to reflexify the whole thing. And so I get rid of KR, I have to put it inside. And I'm putting D in here, so it has to go to the other side. And so what is this map? This is going to be a map from S. Oh, sorry, this is S. And it's going to be KS, right? What I'm going to do is I'm going to move the KR to the other side. But I have to move to the other side by a pullback. And so here I'm going to have KS minus the pullback of KR. So what I have here is RAM. And I put D, and so I have to compensate on the other side. I'm going to have the pullback of D. And 2 RD. Probably very something important, but okay. So I'm using again the plasticity right here. I'm going to take my trace, and I kind of don't like this codomain. So I'm just going to put the codomain I'm looking for, which is RD, by changing my domain appropriately, right? Just like you can move the codomain and domain around. You're flexible to do that. And actually we'll see that I put this as an exercise. I don't know if we're doing it here, because you may complain about this notation because we use this notation for something else, right? And so the point, the point is that the F upper tree of RD, this one here is reflexive. And let's say it's isomorphic to S RAM plus the pullback of T. F upper trig is a great operation. It's going to give you a reflexification right away. And this is why sometimes this is written down, or let's say this is why sometimes this is written down as the F upper trig of T. Or let's say, in other words, this divisor here is often denoted as the upper trig of the divisor D. And this one has a trace, right? If you apply the push forward on both sides, then you have a trace to RD. This is the abstract Rothenberg trace, and this is the one I'm just telling you about. So let me put this as a remark right now, because it's going to be a consequence of what I'm telling you. But this is why I'm calling this trace RD, because it's going to coincide with the Rothenberg trace. It's actually just this. So, okay, so we have this trace of RD that goes from here to there. Okay. Now, what I'm trying to tell you is that how this isomorphism from here to here works. Anyway, here's something important. Right, that's my dream. So I'm going to go ahead and take an element here. Let's take S in there, non-zero, let's say. If it is 0, it has to go to 0. Okay? So S RAM plus pullback D minus E. What on earth does this mean? This means that S is an element in L, right, of non-zero, such that the divisor of S plus this minus this is effective. So if you do the math, that means that this plus 1, this plus this is more than E. That's what it means. An element here is nothing but an element of the field fraction of S, whose divisor, when you add this, is more than E. That's it. That means, another way to think about it, is that if you multiply by S, you get a map from here to here. i.e., in fact, the home of S linear maps from here to here is just given by multiplication by element S that belongs here. Oh, sorry, Wagner again. Oof. Oof. I skip a lot. No, yeah. That's fine. Okay, let me put it like here. But I guess it was sort of a remark. So here we're taking an element S in this round one reflexive module, and I'm just going to tell you that an element here is the same thing as a map from here to here by multiplication by that element. Okay. And what is the next ingredient? Now you compose with a trace of RD, what I just told you about, which is over there. You see that trace goes from, well, I guess I have to put push forwards everywhere. But remember, this is like a dumb operation. And then you land in RD. So that's how you take an element here and you construct a map over here. You take a trace and you multiply by S. That's it. It's all about trace. You see, like every map from here to here is just a trace in some way. You multiply by something. In other words, there is only one way to go from here to here, is through the trace. And it's that trace that we just move it around. That's why the trace is important, because it determines all maps. Okay? And pointed at S to this is an isomorphism of S modules. Any questions so far? I know it's a lot. It's a lot to digest, but because you need to put some effort into going through the calculations. So this is why, again, like any map from here to here is the choice of an element here. Okay. Now, just to finish for today, I'm going to give you another conclusion out of this, and it is the following. So is the other way to think about elements in here. So this is a remark that I haven't done in class, but it's in the notes. So it's the following. So how do you think of an element? So remark. How do you think of an element of RD? By definition, if you have, let's say, R in here, this means that R is an element of the field of fractals of R, such that divisor of R plus D is effective. Unless if R is non-zero, okay? And so you can identify essentially R with this thing here. Let's call it this E. What are the properties of E? E is effective, but it's also linearly equivalent to D. So literally, the elements of here, the non-zero ones, are correspond. So they define effective divisors that are linearly equivalent to D. That's called a linear system, a complete linear system of D. So the remark, and that's why this thing show up in regular a lot. It's impossible in regular three. So I think that if I take a non-zero element here, I can define what I'm going to call the linear system of D, which are all the effective divisors that are linearly equivalent to D. By definition. Sorry, why and so the map, I'm going to take an element R in here, and I'm gonna write E. It's gonna be the E associated to this R. Is gonna be the divisor of R plus D. It is literally equivalent to D because it's just D plus a principal divisor. And it is affected by the definition of what it means to be either, right? This is subjective. That's trivial. But then this map may not be injective. Because two R's may define the same divisor. And actually, we know exactly when that happens. Two R's define the same divisor if and only if they differ by their multiples of one another by a unit of R. So what you see is that the set of units of R acts in here. And they define the same effective divisor. So what I should say is this is an isomorphism after I quotient by the action of units of R. Okay? And so the conclusion finally is the following, is that okay, if I take home in R of the push forward of FSE RT, I'm really check if I want to use anyone. And this ones are disgusting. Is that good? So if we have this, this is in one-to-one correspondence to, well, here I'm going to take the non-zero ones, non-zero maps, and I'm gonna quotient by permultiplications of units of S. This is an S modulo, and I can permultiply by units. So modulo that, this is the exact same thing as the linear system of, let's do the map, round plus the pullback of D minus E. In other words, to a map here, to a phi, let's call it phi, to a phi here, and what I can see where we're at, to a phi here, we're going to map it to a so-called D phi. And this is going to be an effective divisor that happens to be linearly equivalent to 1 plus FD minus E. Or you can put the E on this side and you can say that. And that's it. That's the main conclusion of today. A map here, a non-zero map, is pretty much the same data of an effective divisor dp. We're going to call it dp, that is effective and is linearly equivalent to this. It's an element of this linear system. Well, the point is like, well, any divisor with this property is going to come from here, and two phis define the same divisor if and only if they are a multiple of one another by a unit. Okay? Yeah, that's it. So the data, the important data of a map is recorded by this dp. This is what is conceptually rich, but for the bookkeeping, to do the math, we play with dp. What is dp? Is an effective divisor, right? Linear equivalent to this, but what it is, whatever it is a divisor. It's just, you have to remember a whole bunch of prime divisors with integers. And operations you have to do here that may be complicated will translate to operations you have to do here, but it will boil down to adding integers, you know, the same type of 8 plus 11 type thing, which in principle is much easier. Okay. Maps equals divisors because of this. And so next time, we're going to exploit this in the context of Frobenius. Now you can see what is going to happen. We're going to show up here, Frobenius push forward. S is going to be R. You can put E and D equals 0. And so you can see that the harms we're looking for, if the potential at the splittings, would be divisors. And we'll do that next time, okay? So